Hey everyone, hopefully you can all hear me. Welcome to today's session on moments and resistive forces. So today is going to be split up into two parts as usual. One of the parts will be on moments, the other part's on resistive forces. Actually, the first bit will be on resistive forces. Each half of the session that we do, after we finish it, we'll do a few exam questions to check that we've understood everything we've gone through. And at the start, we'll just do a bit of an introduction of some of the concepts we're going to be using today. Okay, so if anyone has any questions as I'm going through things, just put them in the chat. I'll be keeping an eye on the chat, so just let me know. And if I have time and think I can give a good answer to a question, I absolutely will. Also, I might ask you questions as we're going through the session, just to see how you're getting on with things. So feel free to put any answers to questions I ask in the chat. Okay, so let's go ahead and get started. So today, as I said, we're talking about moments and resistive forces. Just quickly about me, that's a picture of me right there. I'm Matt. And I am a physics PhD student and also a physics tutor. Okay, so let's actually say a bit more about what the objectives of today are. Our plan is to explain the effects of resistive forces on bodies in motion. We're going to try and define moments and define center of mass. And we're going to determine if some pair of systems are in rotational and translational equilibrium. Okay, so hopefully that's all making sense. We should just have a quick issue I need to address. Yeah, okay, we're all good. Perfect. Okay, so let's start by just doing a quick review of some things. Maybe you won't already know these things, but things that would be good to have in the back of your head for today's session. It's broadly just some things about Newton's laws that would be good to be aware of. So maybe the first and most important thing to know about Newton's laws is to know how to state Newton's second law, ideally using algebra. So it says the force is equal to the mass times the acceleration. Now, the important thing here is we're studying some kind of an object with some mass. We want to figure out what the acceleration is going to be. And we say, oh, it's just equal to the force divided by the mass, for instance. Okay, the force is the mass times acceleration. But this is not any force. This is something that's really important to keep in mind. This is not just any old force. The force that appears in this formula is the resultant force, also known as the total force. So it's going to be important today. This is the total, also known as resultant force on an object. So for instance, in this object that we have here at the bottom, we have three forces acting on it, T1, T2, and W. And to find the F that would go into F equals ma, you'd have to add them all together to find the total force. Okay, good. Now, Newton's second law tells us something nice. In fact, it tells us Newton's first law. Newton's first law says if there's no force, then the velocity will be constantly equal to zero, or more generally, just constant. So if there's no force acting on a system, then if there's no force acting on the system, then the velocity will just remain constant. When we have this situation, we will say that our system is in equilibrium. Now, this is a really useful word, equilibrium, and we're going to come across it today in more settings. Actually, when we talk about rotational motion, there'll be a new kind of equilibrium that we'll put together with this one. Okay, good. So let's go back to this picture on the bottom left-hand side of a mass with a few forces on it. I said you need to add them together to find the total force. I didn't say how to do it. So here's how you do it. You take your three forces. So it looks like this one here is W. It's like this one here is T2. It looks like this one here is T1. And you add them tip to tail. What that means is you take the arrowhead of one force and you add it to the back end of another force. So here's the arrowhead, here's the arrowhead. And you do that to all these forces. You connect them together end to end like this, and you see where you end up. Now, this is a very special collection of forces because they end up where they started. This won't always happen. This is what it means, in fact, to be equilibrium. The total force here is zero. The vector we get from putting all these vectors together has no length. It doesn't go anywhere. So maybe let's see an example of a less special example. Let's just focus on one force, say this force T1. Here is another example of vector addition. I could view T1 as being what happens when I add this horizontal vector here to this vertical vector here. Now, not only can I do that, but I can do some more maths here. I can use trigonometry to figure out where each of these vectors must be in length. So in particular, if I know this angle here, then this length here is going to be T1, cos theta. And this is going to be T1 sine theta. Okay, good. When we find a pair of perpendicular forces like this that add up to make our original longer force, we say that what we've done is resolved the vector. So here what we're doing is we are resolving T1 into components. Okay, good. And maybe just a little thing about a very specific force. So the specific force we'll talk about is the weight. And weight is a really prevalent force for us. We exist as bodies just above the Earth, meaning that we are always feeling a gravitational force pulling downwards. The weight is the gravitational force. And this force is defined as the mass times a number called the gravitational field strength. It turns out this number is, that's right here, mg, 9.81 meters per second squared. Now, a funny thing about weight is that if it's the only force acting on us, is that the force is the mass times the acceleration. Therefore, the mass times acceleration is equal to the total force. And if the only force is the weight, that's mg. And this is weird because it tells us, so here we just got some algebra, ma equals mg. We can cross out these m's because they're on both sides, and we find a equals g. Now that might not seem so weird at first sight, but what that's telling us is that the acceleration of any object on Earth is going to be 9.81 meters per second. And that doesn't matter what it's made of. It doesn't matter what size it is. It doesn't matter how heavy it is, in a sense, how much mass it has. It doesn't matter. It will still accelerate at the same rate. Okay, so I think those are the main things we're going to want to know about for today's session. So maybe just before we get started, here are the spec points for the three main exam boards that we're covering today. So there's a spec points for AQA. There's the spec points for OCR, and there's the spec points for AdExcel, which are usually the most concise ones. Okay. So let's get started. As I said, today's split into two sections. We're going to talk about moments and resistive forces, and we'll start with the resistive stuff. Okay, so I'm going to tell you what resistive forces are. And there are going to be two kinds of resistive forces, and it's outlined here on this page already. One kind is frictional forces, and the other kind is drag forces. So let's start by defining them in general. So resistive forces are forces which oppose the motion of an object. The motion of an object. Sometimes the word body is used instead of object. Either is fine. Okay. Say they are always directed in the opposite direction to the velocity. Okay, good. As a result of that, they're forces, so they cause accelerations. We usually think of accelerations as speeding things up, but accelerations can also slow things down, and that's what these are going to do. And because they're slowing things down, we often refer to their effect as one that is causing a deceleration rather than an acceleration. But the deceleration is just an acceleration with a negative value. Okay, so I said there was two types. The first type is friction, the second type is drag, and it all depends on the kind of thing it is that is causing the resistive force. So let's start with friction. Friction is the resistive force due to contact with a surface. Due to contact with a surface. So this won't be true for drag due to contact with the surface. So a weird thing about friction that also won't be true for drag is that friction can actually act on something that's not moving by just stopping it from moving in the direction it would have done otherwise. That sounds a bit weird. We'll talk about it with a picture as well. So as a side note, it can act on a stationary body or stationary object. Okay, so first of all, let's just imagine I have some block. It's moving at some velocity for now, so nothing to do with the stationary stuff yet. And it's in contact with a surface. As a result, it's kind of rubbing against the surface. It's giving away energy to the surface. It is slowing down because of its contact with the surface. There is a resistive force in the opposite direction due to this contact. However, you can actually have a frictional force even when an object is not moving. For instance, if we imagine an object on a slope, we know from experience that if the slope was slippery, if it was made of ice, the object would just fall down the slope. However, we know also from experience that if we have a not slippery surface and we have an object on a slope of that surface, it might not fall down, it might just stay there. There's something keeping it there, and that thing keeping it there is friction. Here, the friction is opposing the motion that would have happened if the friction wasn't there. Okay, now the situation is actually simpler with drag. We don't have this kind of extra feature. So drag is the resistive force due to moving through a fluid. So due to motion in a fluid. Now, fluid is slightly broader than you might be imagining here. Fluid can mean liquid, but as suggested by this picture, you're probably not imagining that this airplane at the bottom is moving through a liquid. You're probably imagining it moving through air. And indeed, gases are also valid fluids. So just be aware of that. When we say motion in a fluid, that could mean a liquid or a gas. Okay, it doesn't act on stationary objects. It's absolutely caused by motion through a fluid. Okay, so a classic example would be something like an airplane traveling through the air. The air is our fluid here. And as the plane tries to move through, it bumps into these air particles. Each time it bumps into an air particle, that air particle exerts a little backwards force on it. All those air particles together exert quite a substantial drag force backwards on the plane, thereby slowing it down. Okay, so those are the main kinds of resistive forces. We're going to focus more on drag now, partly because there's a bit more to say. So, okay, we're going to discuss the factors which affect how much drag an object will feel. You might be familiar with the idea that, for instance, when we're thinking about aeroplanes, we try to make them aerodynamic. The idea is that like drag forces get in the way, they make things less efficient. So we would like to reduce drag if we can. And that's why we design vehicles in a certain way to be a certain shape and so on. So, okay, there are some factors affecting drag. The first one, can't really get away with, is that drag increases with velocity. Faster you move, the larger the drag force will be. So if you're running through the air, you might feel a bit of a drag force. If you're running really fast through the air, it's almost going to feel like a wind. You're going to feel a bigger drag force pushing you backwards. Now, the main one in terms of the design of things that you want to move through the air without feeling drag is about the shape. So another important thing to note is that the drag increases with cross-sectional area. Cross-sectional area. Okay, so what's the idea here? The cross-sectional area is the area that is essentially moving in the direction that the object is moving. So this might feel a bit weird at first. So let me maybe give an example. Let's say this pen says the direction of the velocity of my hand right now. The cross-sectional area of my hand is not this bit you can see here. That bit isn't moving, say, in the direction. It's the bit that's basically perpendicular to the velocity. So the cross-sectional bit here is this entire palm of my hand. Okay. So the cross-sectional area, for instance, of this piece of paper, which is presumably falling down due to gravity, the cross-sectional area is not the area of this side of it here or anything. It is what you would think of as being the area of the piece of paper here. That's the bit that's perpendicular to the velocity. Okay, bigger piece of paper, more drag. So if you can make something that doesn't have much of a cross-sectional area, for instance, you make something kind of pointed, then you have less drag. Okay, the final thing is to consider the kind of fluid we're moving through. So the drag force increases with viscosity. Viscosity. So viscosity of the fluid the object is moving through. So this is another one that we can get from everyday experience. If you imagine, for instance, trying to walk as you do normally, essentially through air, that's okay. Harder is to try and walk through, say, water. Say if you're in a swimming pool or something, you feel that it's harder to walk, and that's because you're trying to move through a fluid which is thicker. So that's a kind of intuitive meaning of viscosity. You're moving through something that is essentially thicker. Okay, so for instance, the drag as you move through honey will definitely be larger than the drag as you try and move through water, which would be even bigger than the drag as you move through air. Good. Okay, so something which is definitely an examiner's favorite is the concept of terminal velocity. So we'll talk about this and we'll do some exam questions. And one of them will be about this. So, okay, the idea that we're going to come across here essentially is that if you account for drag, then you will find that if you drop something from a large enough height and you leave it to fall for long enough, eventually it will reach a constant velocity. Now that's weird to us at first when we've been doing the physics we've been doing so far, because we're used to imagining we have a mass, it has a weight. That weight is a force. So there's a net force downwards. And if there's a net force downwards, then we're going to keep accelerating. We're going to keep on going faster and faster downwards. However, now we're thinking about drag, there's an extra opposing force to keep track of. And eventually we're going to find that an object will always end up moving so fast that the drag balances the weight, so that then the acceleration is zero because the total force will be zero. We said before, the total force being zero. I remember we had a word for that. That means that the object will actually be in equilibrium. Even though it's moving, it's in equilibrium in the sense that there's no total force on it. It's not accelerating. Okay, so let's flesh this out in a bit more detail. We're going to imagine releasing a ball from very, very high up from rest. So we take the ball and we just let go. Okay. Typically, it won't be actually a ball, I guess, in the exam, but it doesn't really matter what the object is. So just call it an object. Initially, this object will accelerate downwards. Why? Well, due to gravity. You might say, well, what about drag? Well, the point is we released it from rest. So initially it's not moving. And if it's not moving, remember the drag is only there if you're moving. So initially it's not moving. The only force this object is feeling is the weight, which is mg, and that never changes. However, as soon as we begin to accelerate, that means we begin to move. We begin to get a velocity. We'll start building up a bit of drag. So this motion will then cause a drag force. Now, nothing accelerates from 0 to 100 without going through all the numbers in between. So to start off with, it'll be moving quite slowly. And because it will be moving slowly, going back to our last page, the drag force won't be very big. So initially, our object starts moving and it gets a bit of a drag force. But still, the force pulling us down is going to be bigger than the force opposing our motion. So we're going to keep on accelerating. We're going to keep on speeding up still in the downwards direction. So speed downwards keeps increasing. However, since we're accelerating downwards, since our speed does keep increasing, the drag will keep on increasing. As the speed gets bigger, the drag gets bigger. So drag will continue to increase. So this is going to keep on going on forever until, well, there's going to be a breaking point here. Eventually, we're going to be in a situation where the drag is as big as the weight. We're moving so fast that the drag is as big as the weight. So in this case, until the drag equals the weight. Here, the acceleration will then become 0. So that's crazy. At this point, we have the acceleration being 0. So our velocity isn't going to change anymore. Since our velocity isn't going to change anymore, our drag is going to stay just as it was. The weight's going to just stay as it was. It's going to keep on being this situation forever. Once we reach this special speed where the drag balances the weight, we will stay at that speed forever until we hit whatever we're falling towards. So we have a special word for this very special velocity at which this happens. It's called the terminal velocity. So the terminal velocity of a falling body is the constant speed that it will reach when drag is equal to the weight. When the drag is equal to the weight. Good. Okay, so I believe that concludes the first half of this session. So feel free just to put in the chat how confident you're feeling. And obviously just let me know if you have any questions about what we've talked about so far. If you are feeling confused, we will be about to do a couple of exam questions that might help. Okay, Atu? Okay, cool. Well, let me know if there's any questions. In the meantime, we have an exam question of our own. And it's a very good one. It's one that is all about terminal velocity, and it's a big 6 marker, as terminal velocity questions often can be, because there's a lot of explaining to do. Okay, so in this question, we're told a steel ball is released from rest above a cylinder of liquid as shown in figure 3. The ball descends vertically in the air and then in the liquid until it reaches the bottom of the cylinder. Okay, so let's see that. We start with a ball here. It falls in the air, yeah, and then in the liquid, right, makes sense, until it reaches the bottom of the cylinder. Okay. Now we're ready for the question. And maybe just before we start, I think it's good to redraw the diagram since it's not here. what did we have? We had the liquid, we had the ball. The ball was going to fall a bit through air and then a bit through liquid. Figure 4 shows how the velocity of the ball changed after it was released. Again, we have a graph here, and at first look, it looks kind of complicated. It's got definitely qualitatively different bits in it. So we're asked to describe and explain how the acceleration of the ball changed after it entered the liquid until it reached the bottom of the cylinder. Okay. The quality of your written answer will be assessed in this question. There's 6 marks here, and we've been asked to describe and explain. So in all likelihood, there's probably 3 things to describe. Each thing will end up explaining. That sounds like about 6 marks worth of answer. So are there 3 things in this graph to explain? Well, I think there are, because there's this straight bit at the start. Okay. Drawing it over it is going to make it seem less straight, but okay. And then there's this kind of point where things change, and suddenly we're going downwards with quite a big gradient. And then we seem to kind of taper off. So it seems to be these 3 things to explain. Okay, so first of all, we just have to describe each one. And maybe the key thing in this question is to know what is the gradient of a velocity time graph? This is going to be key for us to answer this question. We've been given a graph of velocity against time. We're being asked to describe and explain how the acceleration of the ball changed after it entered the liquid. Good. Yeah. So this is the key thing here, is they're asking us to describe and explain how the acceleration changed over time, and the acceleration is the gradient. So let's put that in a box at the top. I think that's important. Acceleration. I can never remember if acceleration is 1c or 2. Ah, yeah, 2. Smashed it. Acceleration equals gradient. Okay, good. So let's start from the top. Situation 1, what can we say? The gradient is constant. So that means the acceleration is constant. So that's the first thing we can say. Before, while I'm writing this, maybe think to yourself, feel free to try putting in the chat, oh, why would the acceleration be constant here up until T1, up until the point when the ball hits the liquid? Why would the acceleration be constant? It's actually a bit odd, given what we were just talking about. So before T0, the acceleration is constant. Also, we know from the picture it accelerates downwards. So here we have like a positive gradient. So not quite, because let's see. Hasn't reached terminal velocity yet. So once we reach terminal velocity, the velocity will be constant. Here, what's constant? The velocity isn't constant. You can see in this, in between 0 and T0, the velocity is increasing, but the acceleration is constant. So yeah, it's not a terminal velocity thing yet, but we will come back to that. So here the acceleration is constant. And this is a bit weird given what we were just talking about. This is something you'd have to kind of clock in the exam or be aware of. What can we say here? Well, the acceleration wouldn't be constant if our drag force mattered. Because if our drag force mattered, if we were even noticing a drag force, then as we accelerate, as our speed increases, the drag would increase and our acceleration would be changing over time. So here in this first part, drag is negligible. So here, before T0, the acceleration is constant as the air resistance / drag is negligible. I mean, that's the hardest, negligible. There we go. The hardest thing to come up with here. Okay. So that's point one, and the comma separates the description from the explanation. Okay, point two. So, well, maybe let me say a bit more here. The acceleration such drag is negligible, so that total force is always F equals M. Okay. So now let's look at point two. Point two, we see quite a big change in the acceleration now because the gradient has changed. Notably, the gradient was positive before and is now negative. So maybe the first question here is, what direction is the new acceleration? Positive. We know before we were accelerating downwards, and that was positive. It's telling us after we hit the liquid, now the acceleration becomes negative. That must mean upwards here. We must mean the direction flipped. So once we're in the fluid, the acceleration is flipped. So after T naught, the acceleration switches and is upwards. Okay, why would there suddenly be an upwards acceleration? Because we're in something viscous now, so we're going to really feel the drag here. There's going to be a big drag force, so big that it's actually bigger than the weight in this case. So there'll be an acceleration, it switches and is upwards. This is due to increase in drag due to increase in viscosity. Yeah. Viscosity. Okay, now let's look at point three. So point three is all about how we tend towards a constant velocity. So that's going to be the terminal velocity bit here. So let's see what happens. Well, first of all, we'll just say what happens. Acceleration eventually tends towards zero, giving us a constant velocity. Okay, why is this? This is because this is since the upwards acceleration due to drag being bigger than the weight causes speed to decrease until drag equals weight. Good. Okay, so in this case, once we entered the fluid, the drag was so big that it was actually slowing us down. But as we slowed down, that caused the drag to decrease until everything was balanced again. Okay, good. So let's go on to the next half of our session, and we're going to talk about moments. Okay, so this is now going to be all about essentially rotational motion. So let's go straight in. We're going to talk about the turning effect essentially of a force. So here in this picture on the right-hand side, we have a force. The force here is the weight of this kind of extended object. But this extended object is fixed somewhere. It's fixed at this point here. And as a result, this force is going to cause it to kind of spin. And the turning effect, the kind of spinning force created by a normal force, is called its moment. So the moment of a force about a point is the rotational the rotational effect of the force. That's not a formal thing. That's just intuitive words. The formal bit is this. It is the product of force and perpendicular distance. And perpendicular distance. Perpendicular distance to where? Perpendicular distance, we actually ran out of room here, sorry for that. Between the line of action of the force and the point. So whenever you calculate the moment due to force, you have to calculate it with respect to some fixed point. So for instance, I could calculate the moment due to this force W with respect to the point I singled out before. And to do that, I would have to find the line of action of the force. That's just the line that goes parallel to the force here. Okay, and I need to find the distance between that line and the point, the shortest distance, that is, which will be this perpendicular one here, perpendicular distance. So let's say that this distance here was d, then in this case, the moment would be simply, let's call it m. M would simply be force times that distance. And that is always what it will be. Okay, so as kind of a bit of a side track before we deal with moments and talk about rotational equilibrium, just a quick extra thing. There's a definition you might come across called a couple. So what is a couple? A couple is a pair of balanced forces. Balanced forces applied at different parts of a body. Applied at different parts of an object. Now that's important because, well, if I had a pair of balanced forces and they acted at the same point, we know from Newton's laws, they'll do nothing. You wouldn't even notice them. However, if you have a pair of balanced forces and they're acting at different points, the object that they're acting on won't shift to the left or shift to the right because the forces are balanced, but it will be able to spin now. So you'll notice the turning effect of this pair of forces. Okay, so they cause a moment. And when a moment is caused by a pair of forces, we give it a special name. We say it's called a torque. Good. Okay, so you can calculate the moment due to this pair of forces. You do it just like with any other one. Actually, it's simplest to choose the point you're calculating around to be where one of the forces is, because then that force causes no moment, and the total moment here is just F times D, F times the distance between the two forces. We'd have got the same result if we calculated the moment around this point. We'd have still got FD. And we'd get the same result even if we calculated the moment at the middle part here. Here, one of the forces would be contributing FD over 2, F times half the distance. And the other force would contribute force times half the distance as well. So altogether, you'd again get F times D. So the point I'm getting across here is for a couple, the moment is independent of where you take moments from. It doesn't depend on the point you pick. That's not true for moments in general. It's only true for a torque or a couple. Okay, good. So the reason we care about moments is the same reason we care about forces. We care about forces because we understand that when they're balanced, nothing happens, and that lets us calculate things. So here we're going to have to go through the same kinds of ideas as we did for forces, talking about the total moment or resultant moment, and then talking about rotational equilibrium. So let's define the resultant moment. The resultant moment around a point is the difference between the sums of clockwise and anti-clockwise moments. Okay, so just like if I have an object and I have a load of forces to the left and a load of forces to the right, I could add up all the ones on the left, take away all the ones on the right, and I'd find the total force. It's the same here, but for a rotation. I have some extended object. I look at all the things that are pulling it this way, all the things that are pulling it in the anti-clockwise direction, find the difference between them, and that's the total moment. So we'll look at an example, but first of all, the reason we care is the principle of moments, which states that an object is in rotational equilibrium if about any point the sum of clockwise and anti-clockwise moments vanishes. Okay, so this is just saying if the sum of all the moments clockwise balances all the moments going anti-clockwise, we will rotate. Rotational equilibrium is basically fancy words for will rotate at constant rate. So if it wasn't rotating, it will stay still. It will continue to not rotate. If it was just already spinning at some rate, it will just keep on doing that. Just like if there's no force on something, it will keep on moving at a constant velocity. Okay, so let's look at a very explicit example now. Let's say we want to figure out this distance d here, and I tell you that this entire object is in rotational equilibrium. I tell you, for instance, that it's just staying still. Then you know that the clockwise moments, here what's pulling it clockwise, well, let's take a point around first. Let's take moments around here so I don't have to care about this thing. The clockwise moments here are 3 newtons, that's a force, times the perpendicular distance, which is 2 meters. Here we have 5 newtons, and the perpendicular distance is d, so that's 5 times d. So I've written an equation here to say the clockwise must equal the anti-clockwise. So here we have 6 over 5 equals d. In other words, d is equal to, what is 6 over 5? Yeah, 1.2 meters. Good. Okay, so before we go ahead and do some exam questions, just a kind of nice conceptual point that's very handy, that, to be honest, if you hadn't thought about, you might not have thought of these things ever being different anyway. But the good news is there's going to be a punchline to this slide. We're going to introduce 2 kinds of point, and then we're going to say that they are actually in the same location. If you hear either of these words, center of mass or center of gravity, you can safely assume they're in the same place. Okay, so first of all, what is the actual definition of center of gravity? It is the point from which its weight acts. Okay, if a body's uniform, this point will be at its center. So imagine I have a uniform rod. The point at which we can assume its weight acts is right in the middle here. Similarly, for an extended, say like piece of card like this, we can assume the weight acts from the center. Okay, that's the center of gravity. It's the point at which the weight acts. Then there's the center of mass. The center of mass is the point at which a force acting would not cause rotation. Would not cause rotation. Okay, cool. So what's happening here? Here are two examples of the same rod, and I'm going to put the same force, but in different places. Here, I'm going to make the force act in the middle. Here, I'm going to make the force act at the bottom. If the force acts at the bottom, it will make this rod spin. However, if the force acts in the middle, it won't make it spin. After all, if it did, which way would it spin? Clockwise or anti-clockwise? You wouldn't even be able to choose. So this force on the right-hand side is acting in the one position where it won't be causing any kind of rotation. This is the center of mass. Sometimes this gets called COG, center of gravity. And as I said, the punchline, which you don't need to be able to prove, but you need to know is true, is that these 2 points are in the same location. So if someone says somewhere is the center of mass, you can assume that's where gravity acts. Similarly, if someone tells you somewhere is a center of gravity, then you can assume that a force acting at that point wouldn't cause rotation. Good. Okay, so how are we feeling about this? Any questions? Okay. Oh, sweet. Good. Okay, cool. Well, let's do some questions. Let's start with this one. Awesome. So this is figure 2. It shows an apparatus used to locate the center of gravity of a non-uniform metal rod. Okay, figure 2. Yeah, so we see a non-uniform rod. We see a couple of wires that are holding it up. We see a Newton meter. Okay. The rod is supported horizontally by 2 wires, P and Q, and is in equilibrium. State 2 conditions that must be satisfied for a rod to be in equilibrium. So remember, we have 2 kinds of equilibrium now. We have the force kind and a new one. So I'll write one, the force one, maybe pop in the chat what the other condition for equilibrium is. So the first condition is the total force on the rod must be 0. What's the other condition for equilibrium? It's not the only one now. It's the other condition. Any ideas? Okay, so we have a new thing, which is all about rotation. So the other thing is that the clockwise moments must, I can't spell that, must balance the anti-clockwise. Yeah, perfect. So sum of clockwise moments must be equal to the sum of anti-clockwise moments. Perfect. Nice one. Clockwise moments. So if someone tells you for now an object is in equilibrium and they don't qualify that any further, you may assume that that means both that the total force is 0 and that the total moment is 0. Okay. Okay, so question B. Wire Q is attached to a Newton meter, so the force on the wire, the force the wire exerts on the rod can be measured. The reading on the Newton meter is 2 newtons and the weight of the rod is 5 newtons. Okay, this is not in the diagram, so we should draw it in the diagram. The reading on the Newton meter is 2 newtons. Okay, that means the force here, the tension in this wire is 2 newtons. The weight of the rod here, that's 5 newtons. Calculate the force that wire P, so this is the one they want, exerts on the rod. Okay, so here we're going to be using the first of these principles. We're in equilibrium. We know that the upwards forces, which is F plus 2, must equal the downwards force, which is 5. So that implies that the force due to P is 5 minus 2, which is 3 newtons. Good. So There may be no prizes for guessing what piece of information the next question is going to ask us to do. They asked us to state two conditions. We just used one of them for part I. Let's see what they want for part II. So for part II, they want us to find the distance D. Okay, they want us to find this distance here. And this is a classic. We looked at an example like this earlier. You have an unknown distance on a rod. You have a load of balanced moments. You can use that to find the unknown distance. So we have to make a choice here, and any choice will work, but some choices will make our lives easier than others. Almost all, because you have to choose where to take moments around now. You have to take a point to take moments around it. And you could choose any point on the rod. However, you should basically always choose a point where one of the forces acts. So I'm going to choose this one here. Why should I choose that point? I should choose that point so that I don't have to care about this force. If a force acts through the point you're taking moments around, it doesn't create its own moment. So you can just ignore it. Okay, so what are the clockwise moments here? Well, I've got the 5 newtons weight of the rod acting at a distance d from this point. So I have 5 times d. That's the clockwise bit. What about the anti-clockwise bit? Well, I have a 2 Newton force taking me anti-clockwise here. And that's acting at 90 centimeters. They've given us that. Perfect. 2 times 90. So should we keep this in? Yeah, let's keep this in centimeters. Okay, 2 times 90. So because I kept that distance in centimeters, the distance d I get from this calculation will also be in centimeters. All right. So let's rearrange. D is equal to 2 times 90 over 5. So that's 180 divided by 5. That's going to be 36. And remember, as I said, as I warned, this was centimeters. This final answer is also in centimeters. Good. Hopefully it's making sense. Next question. Define the torque of a couple. Now, there are all sorts of valid answers you could give to this. I'm going to say the following. The torque of a couple is Fd, where F is the size of each force, and d, the distance between them. Distance between them. Recall that a torque was a pair of forces separated by a distance d, acting on an object in opposite directions. Okay, next question. Explain why the moment of the force and the torque of a couple of the same unit nm. Well, let's just say what the moment is. The moment is force times perpendicular distance to a point. They want to know why they're both newtons meters. So both are a force times a distance. Good. Okay. I remember, in fact, we said that the torque is just a particular kind of moment. It's basically a sum of the two moments created by these two equal opposite forces at different points. Okay, part C. Figure 4.1 shows an irregular shaped metal plate of constant thickness that can be swung freely around point P. Okay, so we're swinging around this fixed point. So if we're going to calculate moments, it will probably be around there. The weight of the plate is 6 newtons. That's in the picture. Good. With the plate in the position as shown in figure 4.1, calculate the clockwise moment of the weight of the plate around an axis through point P. Okay, so that sounded complicated when we said it out loud. But it's lots of words. Clockwise moment. Okay, what of the weight of the plate? That's this thing here. Fine. About an axis through point P. So they want the moment of this force around this point. Remember what we do? We find the line of action of the force, which is this one here. And then the perpendicular distance, which is this one here. And lo and behold, they gave us that already. It's 0.4 meters. Okay, so the moment is going to be the force, which is 6 newtons times the perpendicular distance, 0.4. Chuck that in a calculator and you'll get 2.4. And indeed, the units will be Newton meters. We multiplied a force by a distance. Explain why the moment of the weight reduces to 0 when the plate reaches the bottom of the swing. Okay, let's draw this because I don't think it's immediately obvious at all. Okay, so it's hard to draw, but I think it would look something like this once it's swung to the bottom. But the point is when it reaches the bottom of the swing, what that means is it means when this center of mass that they've drawn here is at the lowest point. Let's give this an X symbol. It's going to be when that is at its lowest possible point. And when it's at its lowest possible point, the idea is it's going to be directly underneath the point it's swinging around. Why is that important? Why is there no moment? Yeah, good final question, actually. Why does the weight here, let's draw it in another color maybe. Why is the weight here, mg, not causing a moment around this point here? Why is the, or in other words, why is the moment 0? Maybe that's a better way of saying it. Okay, so the moment here is 0 because the line of action of the force is where the point is. So the distance between the point and the line of action of the force is 0. And therefore, this number here is going to be 0, and the whole moment is going to be 0. Now, so it's because the distance between the line the force is acting on and the point we're taking moments around is 0. The point is actually on the line. It's not away from the line. It's actually on it. So that means that when we do this force mg times the perpendicular distance, well, here the distance is 0. It's nothing. Okay. So let's write this down. The weight is directed through P, and so perpendicular distance is 0. Okay, I see I have some questions about this still. So since we have a minute, yeah, I think this is a good thing to chat about. Okay, so let's look at 2 situations. Situation 1, situation 2. And these are basically the situations that we had in this question. Situation 1, we imagine that we have a force acting over here. Then we want to calculate its moment at this point. What we do is we draw the line of action. And then we find the distance between that point and the line of action. The shortest distance, the perpendicular one. The shortest, one way of thinking about perpendicular, maybe that's an easier way to think about it. We're finding the shortest distance to the line of action. And here that distance is some d. So the moment altogether is force times d. Okay, now let's imagine a situation where the force is actually acting directly underneath the point. Let's go through the same process again. We're going to draw the line of action of the force. And this time it passes through the point. So what is the distance between the point and the line of action? What's the shortest distance? Well, at 0. They're already in the same place, so there's no distance between them at all. If we were just slightly off, it would be a tiny distance. We're right on the line, so there's just no distance at all. And so this distance is 0. Therefore, the force times distance is the force times 0, which is going to be 0. Feel free to let me know if you still have questions about that. Just for the purpose of time, while I'm looking at the chat, I will just wrap up. So you should now be able to explain the effects of resistive forces on bodies in motion. You should be able to define moments and define centers of mass. And you should be able to determine if systems are in rotational and translational equilibrium. And also use knowing that they're in translational or rotational equilibrium to prove other cool things. Okay, so as I said, I will have to clock off pretty soon, but I'll just keep my eye out for any questions. Did my explanation make sense? Awesome. Okay, I'm glad. Okay, good. I think we'll probably have to wrap it up there then. So yeah, thanks very much everyone for coming. Thanks to everyone who's interacting in the chat. It's super useful for me. So good luck everyone with any homework, any problem sheets, any exams, mock, otherwise you're doing. And I'll catch you at the next session. Oh, just to check, when the line of action goes through the weight, the smallest distance. Almost, when the line of action goes through the point you're taking moments around. So just replace the word weight there with the phrase, the point you're taking moments around. That was the, that was the key thing here. The line of action in part 2 here went through, it always goes through the weight, but the point is that the smallest distance is 0 when the line of action goes through this point, the point you're taking moments around. Yeah, good. Okay, sweet. Thanks so much everyone for coming. Hope it was useful, and I'll catch you all at the next one. Okay, bye.